Welcome to the presentation on dot matrix LCD units. These are often referred to as alpha-numeric LCD displays, and these can be found in commercial applications and commercial appliances such as vending type of appliances. They could be found in, say, coin-operated appliances as well. One of the things that I want to do first is go over the features of them and then look at the pertinent information such as the pinout, take a look at how we would interface them to the 68C11, see what we need to do in order to get them up and running with our 68C11 microprocessor. So some of the features are shown here, and one is that they can be interfaced with either a 4-bit or an 8-bit data bus. Now our 68C11 has several ports on it, and since it does have 3 8-bit ports, we can just use one of those so that we can send 8 bits of data to the LCD. Now with that, if we were to do it through a 4-bit data bus on the LCD module, then one thing that hopefully would be apparent that it's going to take us twice as much code to accomplish it doing it 4 bits at a time versus what it would do just 8 bits at a time. Some of the other features here are that you do have a display data RAM, which is also referred to as DDRAM. You also have a character generator ROM. Now this right here is basically read-only memory that's inside of the LCM, and it has 160 different 5x7 dot matrix character patterns already stored there. So in a sense, it has an Ascii chart that is internal, and so therefore we can just tell it which of those patterns, which of those characters we want to show up on the screen, and they will be shown then. Now with that stated, we also have a character generator RAM, CGRAM, and this allows us to create our own custom characters, and the process of doing that will be shown a bit later. Now DDRAM and CGRAM may be accessed by the microprocessor, so therefore we're able to control those aspects of the LCM. The LCM also has numerous instructions, as you will see, and knowing how or what order of the instructions, okay, to use in order to make our LCM work well with our 68HC11 processor. Now they do have a built-in reset circuit, and they also have a built-in oscillator, so there's not really much that we need to do as far as electronic wise, but we do need to be aware of the pinout. We do need to be aware of the instructions and how we're going to connect it to our 68C11, and then also what we need to do in the code in order to make this LCMs operate. Towards the bottom here, we have a paragraph with very useful information. I would suggest that you pause the video now and read this paragraph. On the second page, we have a block diagram of what is contained inside the LCM. And we have all sorts of things that make the LCD do the operation that it's told to display the data that we want on the screen. What is important to us really is just how will we be able to control this, and these are through the pins that are shown on the bottom of the diagram here, and these are the RS lines, the read-write lines, the enable, and whether we're going to be sending data to it 4 bits at a time or 8 bits at a time. Then about the only other thing I want you to take care of is the power aspect of things. And so we have a VDD pin, a VSS pin, but we also have a V sub 0 pin. That's for the LCD contrast. I would suggest spending a few minutes going over the functional block diagram just as to get better acquainted with the flow of the information. Alright, let's continue on, and let's go and take a look at the pinout. And so the pinout is really found towards the end, so we'll be jumping a few pages here. And let's look at the pinout first of all. And the type of an LCM that we have is a single row pin configuration. And so looking at the table here, we have all the pins that we need to somehow take care of. So let's take a look at these in more detail. You have pin 1, which is the VSS pin, which is going to be ground. And pin 2 on the LCM is VDD. This is where we'll be supplying it with plus 5 volts. Pin 3 is the V sub LC. This is the liquid crystal driving voltage, and this is where we need to do something to this pin in order to adjust the contrast on the LCM. Pin 4 is the RS line. Please note that if it is low, it's going to be receiving instruction code input. And if it's high, it's going to be receiving data input. Pin 5 is a read-write line. And if it is low, then a data write from the microprocessor to the LCM is occurring. If it would be a high, then we're telling it that we're doing a data read from the liquid crystal module to the microprocessor. Pin 6 is the enable pin, and then pin 7 through 14 are 8 data lines. So let's rearrange this table so that we can work with the 68C11 and be able to state which pins will be used on what. Now that we have the table rearranged, let's talk about the pinout for the 68C11. And I'm just going to write 68HC11 up here on top. And these will be the pins that we use. And so for VSS, which is connected ground, really we're just going to connect that to ground on the 68HC11 board. VDD, well, that needs to be connected to the plus 5 volt rail of the 68HC11 board. Let's take a look at pin 3 though. This is the liquid crystal driving voltage. So let's take a look at what we need to do there. Jumping to the last page, we have the contrast adjustment circuit. And one of the things that we need to do then is to come up with something, some sort of a varying voltage at the VLC pin that can be adjusted between 0 and 5 volts, so we can adjust the contrast of the LCD. And again, it can be done as simply as what you see here. Simply have a pot and have the wiper, and at the wiper we'd be able to adjust between 0 and 5 volts, provided of course that the external ends of the pot are connected to a ground and 5 volts on the other side. So just as what you see here, this is something that we need to do. Fortunately, on a 68C11 board, we do have such a potentiometer, and this is called V-adjust. Well, allow me to show you that right quickly. Here's a picture of the 68HC11 board, and we have a potentiometer right at the top right there, and the wiper of the potentiometer is the V-adjust that you see right there. And we have a connector here on the board that is specifically made so that we can insert our LCM pins right into it. Therefore, we really don't have to do any type of electrical wiring or anything of that sort. We just plug it into the connector, and all of the wiring is done for us on our 68HC11 board. So having shown that, then pin 3, that's going to be connected to what we're calling the V-adjust. And that's on the 68HC11 board. And again, it's nothing more than a potentiometer whose external ends are connected to 0 volts at one end and the other end to plus 5 volts. And the wiper is what can provide a voltage that can be varied between 0 and 5 volts, providing the voltage which will adjust the contrast on the LCM. The next we have is pin 4. Pin 4 needs to be sending out either high or low to the LCM, and I'm going to choose to connect that to port A, pin 4, excuse me, PA4, not pin 4, but port A, output 4, PA4. And then for the read-write line, again, there's going to have to be an output from the LCM. And here we're going to be doing data write, so we need to maintain a low right here. We will always be doing a data write from the microprocessor to the LCM. So therefore, I'm going to choose to use pin PA5 for that on the 68HC11. The enable pin is going to be controlled by PA6 on the 68C11. And then you have data lines 0 through 7, and I will be connecting that to port B on the 68C11, so that would be PB0 line, and this would be PB1, PB2, PB3, PB4, PB5, PB6, and PB7. So those are the pins that I plan to use on the 68C11 to be able to talk to the LCM. Since pin 5 is a read-write pin on the LCM, and that's going to be connected to PA5 on the 68HC11. Now, one of the things that was stated earlier is that we're only going to be doing data writes. So that pin will have to be held low. So again, it's a data write from the microprocessor to the liquid crystal module. So in order to be doing data writes, what's involved there? What needs to be happening there? Well, one of the things that we can look at is at a timing diagram. And here we have the read and write timing diagrams. And again, we're only going to be doing a write operation, so therefore let's concentrate on what we have here. And again, just the write operation. So here we have the write operation, and let's take a look at the pins. Here at the top we start off with the RS pin, then we go down to the read write pin, then the enable pin, and then we're talking about lines DB0 through DB7. Now there at the bottom we're talking about the data lines. Now what needs to happen? Well, let me explain just a few things here. I want to make sure that it's crystal clear. Whenever you see in a signal like right here at this spot where you have something that is crossing like this right here means that there is a transition that can occur. Transition that can occur. This is where that line can change state, so on and so forth. After that, during this phase right here, that's where the RS line needs to be stable. It can be either a high or it can be a low, but it really needs to just stay steady. All right. Now the read-write line, same thing. We can have a change here, we can have a change here, but when we're doing a write operation during this whole part right here, it needs to be maintained low. The data values, we're talking about data bit 0 to data bit 7. We can have a change occur here, we can have a change occur here, but see where it says here, valid data, valid data. That means that throughout this area here, this is where the data cannot change, right? Or that it should not change, that you shouldn't change it. Why? Because it needs to be steady, all right, in order to be accepted in. Now, one of the things that we need to see what's happening here is when this data is going to be, per se, accepted, when it's going to be accepted by the LCM. In other words, we need to look at the enable pin to see when it's going to trigger the LCM to take in those data bits and to take, of course, what's on the RS line and the read-write line. If we look at the enable closely here, we can see that when the data is valid, we're actually making a negative going transition right there. And so therefore, when the enable line goes from positive to negative, when there is a negative edge, that's what's going to trigger the acceptance of the data, and also whether the RS line and the read write line are high and low. It's going to accept whatever values are there at that instance. So therefore, we need to make sure that our RS line, our read write line, and all of the data lines are stable when we have that negative going edge. So to annotate our table here, the enable, it's going to be negative edge triggered. So I'll just put a little symbol there, maybe do it like this so it shows a pulse right there. But it's going to be negative edge triggered, and that's one of the things that we have to keep in mind. Now that we have basically the wiring per se figured out, the next thing we need to do is basically what do we have to do in the code? What is the sequence of events that have to happen in order for us to be able to talk to the LCM? And fortunately, this is stated in the handout. So let's take a look at that. Here on this is page 12 out of the 16, we have the examples. The first example, example A, it is an example for sending 8-bit data to the LCM. As it states here, example for the module with a 5x7 character format under 8-bit data transfer. So that's what we're going to be doing. So what this is telling us right here is that we need to initialize the display. There are certain things that we need to configure in order for the LCD, for the LCM to operate the way that we would want to have it operate. And so therefore, there are certain things that need to be initialized. And so that has to be taken care of first before we ever send any values to the screen. So what does this entail here? What is the initialization part? Well, as it states right here on the top, each time the module is turned on or reset, an initialization procedure must be executed. The procedure consists of sending a sequence of hex codes from the microprocessor or parallel I/O port. The initialization sequence turns on the cursor, clears the display, and sets the module onto an auto increment mode. Now, the initial hex code 30, 34, or 38 is sent 2 or more times to ensure the module enters the 8-bit or 4-bit data mode. All the initialized sequences are performed under the condition of register select that it's low and the read write that it's low. Now, the 4-bit data bus microcontroller may operate the display mode by sending the initialization sequence in 4-bit format. Since 4-bit operation requires the data to be sent twice over the higher 4-bit bus lines, memory requirements are doubled. Since we're not going to be doing anything under 4-bit data transfer, we can kind of ignore that for right now. But we do need to initialize it for 8-bit data transfer, and that's following the sequence that we see here. But before we go into what the sequence is and so on and so forth, what is this function set? What is entry mode set and so on and so forth? So let's take a look at the instruction set for the LCM. Here on page 4 we have the instruction codes. So let's go over them briefly. And the first instruction code is the clear display. And we can see that it tells us what the value should be both on the RS line and the read-write line, and also what is going to be the data value that we need to be sending to it. We need to have DB7 be a 0, then DB6 a low, DB5 low, DB4 low, DB3 low, DB2 low, DB1 low, and then DB0 a high. Again, this is to clear the display. As it states under the description, it says clears all display memory and returns the cursor to the home position. Then you have a return home and the value associated with that, but you also notice that it has an asterisk right there. And here, this asterisk is really a don't care. It could be either a 0 or it could be a 1. But what does return home mean? It says returns the cursor to the home position. This is going to be referred to as address 0, shifted to the original position. DDRAM contents remain unchanged. The next instruction is entry mode set, and then the next one, display on off control, the next one, cursor or display shift, function set, and there's a few more others. The best thing is to look at the initialization sequence as to what things do need to be initialized, and then to figure out what the values should actually be. So let's go back to that page. So here, looking at the example for 8-bit data transfer, what the flow chart is showing us here is that, well, one is that we have to power on, and then that we have to have a time of at least 15 milliseconds before we actually send it any instruction. But the first instruction that we need to send, it says here that we need to take care of the function set. Now, they say that it should be a 36 hex, but again, it's the function set that we need to take care of first. But what we need to do now is also start thinking about what is the actual code that we're sending the 68HC11, or the code that's going to be inside of the 68HC11. So that's the thing that we need to also concentrate on at the same time as we're taking care of these instructions. So let's do that. I'm going to go ahead and put the pinout in a vertical fashion, and this should definitely help out. Put that about right there. And now I'm going to fill in all the pin names on top. Alright, just about done. So one of the very first things, of course, we would start off with an origin line. So let's do that. So we have an origin, and let's say that that's going to be at F800. And we'd probably have to take care of the stack, since we're probably going to be running this under single chip mode. So let's go ahead and load the stack with a value of. And let's place say 0, 0, probably F0 would be okay right there. That'll leave us a lot of space so that we can use our stack. Now at this point, we're ready to look at the values that we need to be sending to port B, and be able to trigger the enabling of that value that's on port B, so the LCM will accept it into itself. So looking back here, the very first thing to look at is the function set. They recommend a 3.8. So let's see what value we should use. It could be a 3.8, but it could be something else as well. So let's jump to that page. Now the function set is about halfway down on this table, and we can see that the RS line needs to be low, the read-write line needs to be low, and DB7 low, DB6 low, DB5 needs to be a high, but then we have a bit that's called DL, and DL, we'll have to look at the bottom of this page here. DL stands for what? Well, here on the bottom right it says DL. If it's a 1, it stands for 8 bits. If it's a 0, it stands for 4 bits. Well, we're going to be doing 8-bit data transfer, so therefore our DL needs to be a high. Going back up, then the next bit is the N bit, and for that one we need to look down as well. And for the N bit, we have, it says 2 lines. We're going to use a 1 right there. So therefore, so far we have a DL that's equal to a 1 and an N bit that's equal to 1 as well. We also need to look at the F. Alright, so the F bit. The F bit here is going to be, if it's a 0, it stands for 5x7 dot matrix, which is what we have. So therefore, the value starting off with DB7, working our way down to DB0 would be 0, 0, 1, 1. Now, that makes the value of 3 in hex. Then a 1, 0, and these other two are just placeholders as far as the asterisk, so it could be a 0, 0. So therefore, you could very easily make that a 38. So what they recommended should work for us as well, because we come up with the same values as well. So we could use a 38 hex. Now, one of the things that I haven't covered yet is the n bit where it says that n is equal to 1, that it's 2 lines. What are we talking about here? Well, there are LCMs that are basically a single line or a single row per se. Some have 2 rows in the display. Some might even have 4. So let's take a look at several different arrangements. Here on page 9, we have the arrangements. Now, one of the things that I want to stress here is that every single character space or character place has an address assigned to it. So for example, if you look at the arrangement called 1 right here, this is for a 16 by 1, which means 16 characters by 1 line. Now, please note that the leftmost character space starts with an address of 80. Then after 8 bits, it changes the address to a C0. So everything's going fine. It starts off with an 80, then 81, 82, 83, 84, 85, 86, 87 hex. But then the next display space has a different address. It's not just it's not just the very next increment of whatever address you had. It's going to jump from 87 and then it's going to be a C0. Now, one of the things that you have to be attentive to is in your code, if you set up the LCM to increment, but if you don't actually tell it a new address right there in that place, then what happens is that you'll keep on sending information to say like 88 hex and 89 hex and so on and so forth, and it'll never show up on the display because you did not tell it to go to that C0 address after you sent it the first 8 bits, the first 8 bytes of data. Now, if you look at the arrangement for 2, that's a 16 character by 2 lines. And again, take a look at the addressing. The entire first line is from 80 hex through 8F hex. But the second line starts at C0 hex. Now, if it was in a perfect world, you'd say, okay, so if I started at 80 hex and went through 8F hex on the top line, you would normally assume that the next line would be starting at possibly maybe a 90 hex, because that would actually be a one more value, okay, or one more increment as to what the address was prior, which would have been an 8F, because a 90 comes after an 8F hex. But in this case, no. So attention has to be paid to that so that you make the proper adjustments in the code so that you can send data to the screen and not somewhere else. Now, for arrangement number 3, you have 16 characters by 4 lines, and arrangement number 4, 20 characters by 2 lines. You also have 20 characters by 4 lines, and if we go further down the page, you can see that we can go all the way to 40 characters by 2 lines or even 40 characters by 4 lines. Now again, please pay attention to the addressing because that's very, very important. Now for the very last arrangement, which is number 7 right here, you can see that you have line 1 and line 2 having the same addresses all the way across. Now one of the things that has to happen is that you will have 2 enable pins, or possibly just 1, which would either be, if it has a 0, it would be on, say, line 1. If it has a 1, it would be on line 2. But they typically will have 2 pins that you will be using to control as to what you're writing to, just as it states here. So it says, note, address locations on lines 1 and 2 are controlled by enabling E1, and then address locations on lines 3 and 4 are controlled by enabling E2. So most will have 2 other pins that you need to control in order to tell as to which line you're sending information to. Now going back to our table here and thinking about some code, so we saw that we could definitely send a 38 hex to port B. Now we would have to have our RS line below, our read-write line below, and our enable line needs to be low to start off with as well. Now, let me annotate this. PA4 is our RS line, PA5 is our read write line, and PA6 is our enable line. Now, one of the things I do want to state is that the function set, okay, in most instances will work fine with a 38, but, and by that I mean is that most LCMs will work fine with a 38, but there are some LCMs that actually respond better to a 30. So if a 38 for some reason is not operating fine for you, and you're still not able to see anything on the screen after you've adjusted everything else, and you're sure that everything else is right, try a 30 hex. That might clear up the problems just fine. All right, so let's take a look at what we'd have to do as far as code. Well, we could then do a load accumulator, and let me change the color on that. So we would load accumulator A, and we could load it with a 38 hex, and then we could store that at port B. Now granted, somewhere above here in the code I will equate port B to address 1004. I haven't actually shown that in this program, but just be aware that you would have to put an equate statement somewhere above to equate port B with address 1004. Now, the other thing also that we need to do is, how do we take care of the enabling? Well, the enabling is going to be done on pin 6 on the enable line. It's going to start off low, and we were talking about a pulse, right? We're talking about a pulse. We're going to send a pulse, which means it's going to be low to start off with. Then we're going to have to set it high, then we're going to have to set it low. And when we go from a high to a low, that's when we're sending a negative edge. And that's what's going to cause the triggering of the information into the LCM. So what we're going to do then on the enable line is we're going to make it high, and then we're going to make it low again. And this here is going to create our pulse, our positive pulse, just as I've shown down there. Continuing on, now while we're doing our pulse, everything else has to be steady, so we'll still have to keep those values that you see there. So once we load accumulator A with a 38 and we send it out to port B, all we have to do is take care of what's happening at port A now. Now, we really don't care all that much about any other pins except just PA4, PA5, and PA6. So I'm going to set all the other pins low. So when we think about all the other pins, as far as what their placement is, we'd have PA7, PA6, PA5, PA4, PA3, PA2, PA1, and then PA0. As I stated, all I want to do is to maintain PA4 and PA5 lows, and then PA6 needs to be a low to start off with, and so everything else will be low. So that really amounts to a 00 hex, and then the enabling, okay, will occur on PA6 where it goes high while everything else is low on port A. And so that comes out to a 40 hex. And then I need to take PA6 low again. So that's going to go low again while everything else is low. And so therefore that's going to be a 00 hex. So these are the values right here that I have to put into the code, but that's going to take care of what's happening at port A. So let me bring this down a bit right here and start writing some more code. So I'm going to load accumulator A with a 00 hex, and let me fix that. 00 hex. Then I'm going to store that at port A. Now granted, I should have an equate statement up above that equates port A with address 1000. So again, make sure that you make note of that there should be an equate statement up above equating port A with address 1000. I have not included that in what I have here. Now with that, I stored it at port A. Then I need to do what? Then I need to send it a 40. So I need to do load accumulator A, and I'm going to load it now with a 40 hex, and I'm going to store that at port A again. Then I am going to load accumulator A with a 00 hex again and store that at port A once more. And so these are the values that are going to take care of my enabling. So again, these are the values here from here to here. That takes care of my enabling. Alright, so now what I'm going to do is just to bring this code down a little bit to make sure that I take care of the equates. I want to make sure that everything's perfectly clear. Okay, at this point I've equated port A and port B at the top of the program. Now we will continue on with the next instruction. So we've taken care of the function set. Now we need to take care of the entry mode set. Now what they recommend is a 06 hex, so let's make sure that that is what we need. Looking at the third row of the instruction codes, we have the entry mode set, and we see that we have a value starting with db7 all the way down to db0, 0, 0, 0, 0, 0, 1, and then we have an I/D. So what does that stand for? If we go towards the bottom of the page, we have I/D. If we set it to 1, it's to increment. If we set it to 0, it's to decrement. What we're talking about here is the addressing, okay? The addressing as to if you want the address to increment as to where it's on or to decrement. And what that means is if the cursor is going to be advancing in the address value, or if it's going to be decrementing. I prefer mine to be incrementing, so we're going to set that one to a 1. So I/D is equal to 1. And then the last thing we need to take care of is the S bit. And the S bit is, do we want the display to shift or no display shift? I prefer the display not to shift and to have just the cursor shift instead. So therefore we'll set the S to 0. So that comes out to being a 06 hex for the entry mode set. Okay, going back to this, we knew that this was having to do with the function set. And the next here is going to be the entry mode set. And we said that we're going to send it a 06. So what we need to do is set this to a 06 hex. And we're going to have to leave it there nice and steady, because why? Because we need to send a positive pulse. And what we're going to do is we're going to start the enable low and keeping the read, write, and the RS lines low. And then we're going to enable it, okay, or excuse me, we're going to set the enable high while keeping everything else low on port A. Then we're going to set it low as far as the enable line. And that is going to give us the negative edge, which we need. And so therefore the LCM will take in those values. So again, going back to the code then, we need to think about what we need to do next. Well, we took care of the function set, so therefore now we have to send port B a 06. So now I will do something like load accumulator A with a 06, and I'm going to store accumulator A at port B. Now after that, I need to take care of the enabling. So in a sense, what I need to do then is repeat the portion that I have in this area. That would be what I have right here. So I'm going to repeat that. So let me take a copy of that and transfer it on further down. Alright, so here we go. So we're going to do the exact same thing again. We're going to load accumulator A with a 06. Let's store it at port B. Now the part that does the enabling is the loading of A with a 00, then storing it at port A, then loading A with a 40, storing it at port A, and then loading accumulator A with a 00 once again and storing it at port A. That takes care of the enable line at PA6. Now that we've taken care of the entry mode set, what else do we need to take care of? The next instruction is the display on-off control, and they recommend a 0E. So let's take a look at this particular instruction and see if the value that they have here is a value that we need to send out as well. Looking at the fourth line down, we have the display on-off control. We can see starting off with DB7 that we have 0, 0, 0, 0, then a 1 at DB3. Then we have a D at DB2. Looking down at the bottom of the page, D stands for display on or off. Well, we want the display on, so we would set that to a high. The next thing is taken care of C. And C is, do we want the cursor on or do we want the cursor off? Well, I would prefer to have the cursor on so I could see it. So I would set that one to a 1. And finally, we have B. Do we want the cursor to blink or not? If we set B to a 1, the cursor will be blink on, which means that it's going to be blinking. And if we set it to a 0, it will not be blinking at all. You won't be able to see it. So if we were to send a 0E, the cursor would not be blinking. And if we set it to a 0F, we would see it blinking. I would prefer to have it to blink on. So therefore, from that perspective, we would have all of the bits be high, both the D, the C, and the B. So I would send a 0F instead of a 0E. So that's what I will choose to send there, a 0F. So for the display on-off control, it's going to be a 0F that I will send. And again, I need to look at what the values are. And this again is for the display on-off control. Okay. Now what we need to do is to do the enabling just as what was done prior. So in a sense, we're going to do the exact same thing that we have here. So let me just copy and paste it, because we're going to do the exact same thing there in the bottom, which means that the enabling code that we copied is going to be repeated again after we sent out the value to port B. So looking at the code, the very next thing would be to load accumulator A with a 0F, and that's going to be sent out to, it's going to be stored at port B. Now the one thing that we're going to do is we're going to be repeating the exact few lines that take care of the enabling. We're going to be doing that again. So let me just copy and paste that and put it over to the side. Now that would be this group of code that you find here. That would be the code that would be repeated. Now one of the things is that I want to bring that over, so let me do that. Alright, so here is this code right here. Now one of the things that I want to emphasize is that after the bottom here, the code would advance to there. Now one of the things that again is very important to kind of show here is that we have a repeating block of code. we have it here. We also have it here, and we also, if I can get this just right, also have it right there. Now, since we have the same chunk of code, and really also if you take a look at each of these chunks of code, right above it we also still have the same instruction. If we take a look at it, we have the store accumulator B. So let me just go ahead and show you what I'm talking about, is that we could just grab that and put it into that chunk of code because it's found before that chunk at every instance. So we have that right there. So in a sense now, since we have repeating chunks of code, that's a perfect opportunity to turn this into what we call a subroutine, right? So what we could do is to take this right here and turn it into just one chunk of code, but it would be a subroutine, and then we can call that subroutine anytime we want. So in the process of writing our code, let's create a subroutine. So let's do that right quick. Let me clean this up just a little bit. And what we need is the store accumulator A. So I'm going to write it here, and I will rearrange it in just a bit. Store accumulator A at port B, and then load accumulator A with a 0, 0. Then store accumulator A at port A. Then load accumulator A with a cross-hash $, that would be a 40. And then store accumulator A at port A. And then load accumulator A with a 0, 0 once again, and store accumulator A at port A. So this is what is inside of these chunks of code that I've annotated here in orange. You have a store accumulator A with port B, load accumulator A with a 0, 0, then store it at port A, then load accumulator A with a 40, store it at port A, then load accumulator A with a 0, 0, and store it at port A. Now, one of the things that I just noticed right here is that I have an H right here in this area, and an H that should not be in the code. So please disregard that part. But because we're going to turn all of those into a subroutine, what I am going to do then is put an RTS, which means return from subroutine, and then in front of it I am going to put a label. So let me just move this over just a little bit right here so I can get this, and I'm going to put the label instruct, because these are instructions, right? So there we go. So it has a label instruction. I turned it into a subroutine. So now in a sense we could remove all this here, all this block, just remove it completely right there, and I can now just cut this out and replace a subroutine with a call to, replace that chunk of code with a call to the subroutine. So therefore I'm going to do something like JSR, and I'm going to call that instruct. And so therefore it's going to jump to the subroutine, call instruct, and this is a chunk of code which you'll run. And I will do for that for all the other ones as well. Now after I'm going to bring the load accumulator A with a 0, 6. I'm going to bring that just up because that still needs to be there. So let me see if I can grab that. And that would be the next instruction here. And then after that, I would do a JSR instruct again. And now I could erase all this code, remove it, and then I do need to take this load accumulator A and put over here, and then just make a call to my subroutine, JSR instruct. So now I have a subroutine in place, and I can erase all of this here, and I can delete that. Alright, so I have my subroutine. Great. Now one of the things that I need to inform you of is that the LCMs, most LCMs run really slow. So running at the speed that we're sending out a value to port A and doing the enabling and so on and so forth, that's a little bit too fast for it. So one of the things that we're going to need to do is to slow it down a bit. Slow it down. So I am going to create a subroutine to create a delay. So I'm going to call this subroutine. Okay, so a delay will be put here, and that's the actual name of the subroutine. And I'm going to load X with a value. And a good value here would be something like a 02FF. That's enough of a delay that things will work properly and there will be no errors or anything like that. So I'm going to go ahead and put that value. I'm going to decrement X, and then I'm going to branch if not equal. I'm going to call this again. So I'm going to have a label of again in front of my DEX. So I'll do that. And then an RTS because it is a subroutine. Now one of the things that I need to do is to invoke or to call the delay subroutine in the instruct subroutine. So I need to go ahead and make some space here. So after I load A and store it, I'm going to put a call to the subroutine. So I'm going to say JSR delay. So it calls it there. And then after it stores it at port A right here, I'm going to put a delay again right there. So JSR delay. And then after it stores it again at port A delay once more. So JSR delay right there. Alright. Now with that, we have two subroutines created, and with those subroutines we have everything that should function as far as the instructions. So let's continue with the instructions. We had just taken care of the display on off control. What's the next one? After the display on off control, we have the display clear, and that's going to be a 01 hex. And if we look at the opcodes, at the operation code, let me just scroll up here, you can see that a display clear, it's always a 01 hex. So let's include that in the code. What it does though, in the description column, it says that it clears all display memory and returns the cursor to the home position. So really that's one of the things that should happen at the very front end, that it clears everything which might have been there, it clears it out. So you basically have, in a sense, like a fresh start, a fresh page to start off with. Now I'm going to have to rearrange a little bit of this and erase a good portion of this. As far as our table, you see the purpose that it served as far as the table on the pinouts. So let me go ahead and remove this and I will remove this as well, and I will take some of this and shift it over. I need to take some of this, put it right here, and if I could take some of this possibly and put it right about somewhere about right there. Okay. Now I'm going to take this code, since this is our main code, I'm going to put it here, and I know that this code here is going to be towards the end of our program, so I'm going to put it on the right somewhere over here for right now. Okay. So we had to do a display clear, so that's the next thing that we need to do, and our display clear would be somewhere here. So let's go ahead and put that in there. So display clear, and then we need to send a 01 hex, right? And we need to do the enabling as well, where they're all lows. Then the enable line goes high, then it goes low. All right. Now this did get a little bit skewed here. Let me pull this up just a little bit, somewhere there, a little bit better. So as far as our instruction here, then we need to do what? We need to load accumulator A with a crosshatch $sign with a 01. And then after that, all we need to do is to invoke our subroutine JSR instruct, and it's going to jump to the subroutine. It's going to store that value 01 at port B, then it's going to do the enabling on PA6, on line PA6, and it'll have the proper amount of time spent after each of the changes on the enable line, so that the LCM has enough time to respond appropriately. All right, so let's take a look once again at the next thing in line as far as the initialization part. And jumping back towards this part right here, we see that the very last thing is, it says here 80 hex, right? And it says a DDRAM address set. Well, DDRAM is really what the addresses are that are on the screen. And as we saw, 80 is the leftmost character space on the LCD screen. So 80 hex is where we need to start off. That's if you want to start at the leftmost place. Now, looking back here, and this is actually going, all right, here's the page for it. And as we can see, if we had a 16:1 type of display, or whether it was a 16:2, all of the every single leftmost value, okay, or each one of the LCMs has a leftmost value that's called 80. Granted, for the ones that have two lines, that would be the leftmost value on the first line, but they all start at 80. Now, if you wanted to start somewhere else, like if you wanted to start at address line, say if you're looking at the 16:1 LCM, if you want to start at address, say like 85 or 86, or if you want to start at address C0, which is in the middle of the display, if you want to start there, that would be perfectly fine, but just that you need to tell it what address you wanted to start on. In most instances, I would start it at 80, so I will start there. So the next line of code here would be load accumulator A with an 80, and then do a JSR instruct. Now what that does for me is that now it knows that whatever data, as far as actual data that I sent to it, it's going to show the ASCII representation of that value at address 80, which is on the LCD screen itself. Well, here we're at the point that we can go ahead and start sending it some actual data to display. So let's take a look at the Ascii chart. And here we have what we call the character codes. And so these are all of the characters that are stored in the ROM. And so therefore, why don't we pick out a value? Say if we just want to send, say, an A and then maybe a C and a C. Now granted, you do have uppercase and lowercase, so you have to choose which one you actually want. So for example, if we wanted to send out a capital A, and so therefore the value, as far as hex value, that would be a 41 hex. Again, if you look at the on the column that where the capital A is found, that column at the very top has a 0100, and that's a high order 4 bits. Now just convert that to a hex value. That right there, a 0100, is a 4 hex. And then if you look at the column value there on the left, you have a 0001. That's the lower hex value, and so that's a 1. So if you put those together, you end up with a 41 hex. So let's just say that we wanted to send out the text ACC all in caps. Just again, ACC. So we know that for an A, it's going to be a 41, and for a capital C, it's going to be a 43. It'll be a 43 hex. So let's look and see what we need to do to take care of sending out ACC and put that on the screen. Alright, so we stated that a capital A is going to be 41 hex, and that a C is equal to a 43 hex. So let's just keep that in mind so that we don't forget. We could of course look back on the charts. Now, after we sent out all the instructions and we told it what our starting address on the screen was, now we can actually start to send it data, but we're going to be sending it as data, or in other words, we have to do the enabling, okay, in such a way that the LCM knows that it's data. That means that what? That means that our RS line, okay, our RS line, which is on PA4, that line now needs to go high. That needs to go high. So therefore, the values that I would have here would be that PA4, the RS line, now needs to be a high, and these two values, as far as the enable and the read-write line, those are lows for this instant. And what do I place on port B? Well, I'm going to send that 41 hex value. That's what I'm going to put on there. Now, the other thing that I need to do is, once I put that at port B, then I need to take care of the enabling. This is where I send a high to the enable line, leaving everything else as is, and then putting a low on the enable line, thereby creating a negative edge. And so therefore everything else stays as is, and this is taking care of the capital A. All right, the capital A. So as far as code wise, what is it that we need to do? Well, we need to load accumulator A with the value of 41 hex. And after that, we can go ahead and tell it to do the enabling. But here's the thing, that we cannot tell it to do the enabling that is for an instruction. Okay, we have to come up with a different enabling, because you see that the RS line now is a high, while the instruct enabling, your RS was a low. So therefore we need to come up with another subroutine, and the subroutine, I'm going to call that one data. So let me just move all of this here a bit further down, because I'm going to put the data subroutine on top of this. Now the interesting thing is that everything else pretty much stays as is except the actual value that we're sending, because the only change was actually what? The only change here was in this area, your RS line. Your RS line changed from a 0 to a 1. So that's the only thing that changed. So what I'm going to do is I'm going to copy all of the instruction subroutine and just make those changes. And I actually meant to copy it. And let's put this up here. Now one of the things I need to do, of course, is I need to change what the subroutine is called. This is going to be called data. And perhaps I should have done that in a different color. There we go. Data. And what are going to be the values that we sent out to it? Well, here's the thing, is that PA4 needs to be a high. So therefore, what do we need to do? Well, we can again put down all the bits. That's PA7, PA6, PA5, PA4, PA3, PA2, PA1, and PA0. And if we take a look here, PA4 needs to be a high, everything else needs to be a low. And then PA6 needs to go high. That's the enable line, right? Because this is our read-write line, and this is our RS line, while everything else stays as is. And then the enable goes low again, while everything stays as it was. So these values are going to be what? Well, this is going to be a 10 hex as far as this line here. This one right here is going to be a 50 hex, and then it's going to be a 10 hex again. So those are the values that I need to put into my data subroutine. And so that everybody's clear, I'm going to put a different color for where the changes were made. This is now a 10. And this value here is now a 50. And this value is now a 10. So we've created our data subroutine. So great. So let me go ahead and remove some of this and continue with our code. So the first thing I need to do then is, since we loaded accumulator A with a 41, we're ready to call our subroutine. Okay, so JSR data. That takes care of enabling actual data that will be sent out to the screen. So we took care of that. So this right here, we put a comment. That's going to be an A that's being sent out. And now we can tell it to send out our next value, which is a C. So I'm going to load accumulator A with a 43, and again that's a C. Okay, that right here is a semicolon, and then after that, JSR data, calling of the subroutine, and then I'm going to send one more C. So again, I'm going to load accumulator A with a crosshatch $43, and again semicolon, and that's a C. And don't forget that the semicolon, anything after a semicolon means that it's just a comment. And then after that, invoke or call the subroutine data, and so it calls it out. And then after that, you should see ACC on the LCD being shown. Now after this, the best thing to do is, since there's nothing else that we really wanted to accomplish at this point, we weren't trying to do per se inputs off the push buttons or anything like that. All we wanted to do was just to show ACC on the screen. We need to figure out some way to have a controlled ending. And the best thing at this point is to put it into a controlled, well, I wouldn't call it controlled. It would be just to put it into an endless loop. That is a controlled ending for our program. So I'm going to put it into an endless loop. So here I'm going to tell it to branch. I'm going to tell it to branch per se something like over, and I'm going to put the over label in front of that. In order to run this program in single chip mode, there is one more thing that needs to be done, is we need to take care of the reset vector assignment. And we can do that by putting one more origin statement, one more origin line at the end. And that would be origin FFFE, and then form constant byte F8, comma, and then 0, 0. So what this does, it takes care of the reset vector assignment by placing an F8 at FFFE and a 0, 0 at FFFF. And to make sure that the flow of the program is definitely understood, the start of the program is up here. That's the start. And then from here, it would go up there. Thank you.